Hello everyone! In this video we will continue to examine topic 1.2, uncertainties and errors. So, in the last video we described a example where measurements might vary. And we began to unpack sort of why measurements could vary. The first thing we discussed was the idea that the quantity in question could itself actually be varying. That's known as intrinsic variation in the quantity. But there are also, straightforwardly, errors in measurement. So not all measurements, and in fact, no measurements, will 100% precisely measure the real or the true quantity, okay, whatever the value is. The one exception being discrete quantities. So if you're literally counting something, you can have zero error. And error is formally known as, or formally means the deviation from the real or the true quantity. Notice this is a precise use of the word. This does not line up with ordinary English, where we might say something like, well, I made a mistake, I made an error. That's not the same use of this word, although obviously they're related. In this case, we say the error on the measurement, meaning the deviation from the real or the true quantity from the measurement. The real or true height of the real or true time it takes for the ball to fall might be something like 0.9 seconds. If you measure 1.2, your error on that particular measurement is 0.3 seconds. It's how far away you are from the real or the true quantity. Now, error comes in different types when you take many measurements of the same thing. It's important to recognize that this distinction, the one I'm about to discuss, the distinction between systematic and random error, is a distinction that only makes sense if you're taking multiple measurements of the same data point. If you take a single measurement of a physical quantity, it will have some error. It'll be off in one direction or another, but neither the word systematic error nor the word random error will apply to it. Okay, they simply won't make sense because systematic and random error are things you discuss when you take multiple measurements. Why? Because the definition of a systematic error is an error that systematically occurs always in the same direction. Okay? And you can introduce this type of error, known as systematic error, in a lot of different ways. So one way you could do it is with a methodological error, as in the case of reaction time. First of all, we wouldn't say that reaction time is a systematic error. We would say that reaction time introduces systematic error. And this error is always in the same direction. If you're reacting to the ball hitting the ground, let's say you've got your back turned and you're simply listening for the sound, then the reaction time will be a methodological error. It's not due to the instrument, it's due to the method that you're using, and all the times that you measure will be too large. They will be too large by sort of different amounts, so you got to be a little bit careful about that. But every time you measure the time, if you have your back to the ground and you're simply listening for the ball to hit before pressing the button, you will have a systematic error. All your times will be too large. This error is in the same direction every time. Okay. Another way of getting systematic error is instrumental. So let's say you're measuring those heights and your ruler has, unbeknownst to you, been cut off at the bottom. So you don't know it, but the ruler, which is supposed to measure a meter, starts at sort of 1 centimeter and cuts off that first centimeter. Then all your heights, all of them, will be measured. Actually, in that particular case, all the heights will be measured to be too high. Okay, so the height you write down is higher than the actual height. So this is probably a little misleading in the notes here. So I'm actually going to adjust that. All right, so all the heights are too high. Another example of a systematic error is a calibration error. So as some of you who have used sort of scales or balances know, often you need to zero the instrument. You need to set zero to where it's supposed to be. And if zero is not where it is supposed to be, if it's reading zero when, for example, 15 grams of mass are sitting on the scale, then you'll have a calibration error and your values will be off, and they will always be off, always in the same direction. And here's the key, okay? And I'll mention this more later, but if they're all off in all the same direction, taking more data doesn't help, okay? And that's usually a key that you've got a systematic error, is that it is systematic. It happens every time and always in the same direction. Notice, I really don't ascribe either of these as systematic errors. Instead, the way we say it is these problems, these sources of error, introduce systematic error into our measurement. And so our measurement has systematic error. Now, the other category of error is random error, okay? And that's error in different directions or multiple directions. Notice this type of error does not make sense to apply to a single measurement. If you're off by, let's say, 0.3 seconds in your measurement of the time is supposed to be 0.9, it is 0.9, but you have measured 1.2, then that is in one direction, but that is a single measurement. So it doesn't even make sense to say that that would be due to random error, nor does it make sense to say that would be due to systematic error, because even if there is some systematic problem, the errors aren't going to be in the same direction. There's not multiple errors to measure there. So random error is error in different directions, and it basically refers to the unavoidable scatter in your data. That is, with any sort of continuous measurement. So with discrete measurements, you can say, okay, there are exactly 5 here, not 6 and not 4. But with any sort of continuous measurement, you're going to get some random error. And it might be larger, it might be smaller, but the spread is related to that random error. Okay, so let's say you're measuring the times and you have both reaction and anticipation time problems. You have both issues, which is quite likely. Well, some of the measurements you'll take will then be too long, and some of the measurements you'll take will be too short. And if these problems are at about the same level, okay, then you will have error away from the true value in both directions. So it's not that reaction time is always systematic. It's that in the example, if you sort of describe the source of error, you consider, is the error giving you error in different directions? If the answer is yes, it's introducing random error. If the answer is no, it's systematic. Here's another example. Reaction time on both the start and the stop of the drop. So everybody knows that you might have some reaction time to seeing the ball hit the floor, but very few people remember that in order to time the original start of the stopwatch, you will also have some reaction time there if someone is sort of counting down. Both of those are examples of methodological ways of introducing random error. Notice that you can also have random error from a stopwatch. So there is going to be some instrumental random error that is due to the precision of the stopwatch, that is, the number of digits the stopwatch shows. It's not going to be infinitely precise. It will only show so many digits. And so some of the scatter in a particular measurement, that is the deviation from the true value, will be a little bit higher than it would be otherwise, or a little bit lower than it would be, due to the fact that that stopwatch is only measuring to a particular number of digits. Notice how both systematic and random error can be either methodological or instrumental. Okay, so there is no necessary connection between the instrument and the random error and the methodology and the systematic error. This is something that is often conveyed by physics textbooks, which is quite misleading.